Okay, welcome. This is Mr. Dahlstrom going over some AP physics problems. Unfortunately, these are the problems that I had already recorded, but when I was doing it through Zoom, Zoom decided not to convert the video file, so I have a nice, awesome video that has no video to it. It just has audio, so it pains me to do it, but I'm going to go ahead and do it again. I'm going to go a little bit faster here because it is a video, and you can take as many times you want to go over it again and again. So I did go over this on last Friday, so that would be October, whatever that Friday is, October 2nd. So what we looked at is three problems. Let me go ahead and refocus my camera here. We looked at number 52, 53, and number 64. 52 and 64. 64 definitely takes a little bit longer amount of time. So 52 says, consider a large truck carrying a heavy load such as steel beams. A significant hazard for the drivers that the load may slide forward, crushing the cab. If the truck stops suddenly in an accident or even in braking, assume, for example, that a 10,000 kilogram load sits on the, up here, so it sits on the flatbed of a 20,000 kilogram truck, moving at 12 meters per second. Assume that the load is not tied down to the truck, but has a coefficient of friction of 0.5 with the flatbed of the truck. Part A, calculate the minimum stopping distance for which the load will not slide forward relative to the truck. And B, is any piece of data unnecessary for the solution here? So this is one of those problems where if you look at the first thing they ask you, they're asking about distance here, and you're like, how do I even get distance? You have to go through amount of work to, the first thing we need to figure out is if we know the initial velocity. So I actually have the work written out. I don't know if I want to really write it out from a third time, but I will kind of go through what I have here. So disregard these numbers up here. These are problems I went through before. So this is number 52, and you have your truck here, and you have your beams there. It says that the beams are 10,000 kilograms, and it says that the mass of the truck is 20,000 kilograms. They tell you that the initial velocity of the truck is 12 meters per second. It then slams on its brakes and comes to rest, and we have to figure out the minimum stopping distance. So we need to figure out what delta x is, assuming that we know the initial velocity. So the final velocity here is going to be 0. So let's just write out a little bit further what we actually know to figure out what we're going to have to figure. So we know the initial velocity is 12 meters per second. If it's coming to a stop, that means the final velocity is 0 meters per second. And we're trying to figure out what delta x is there, but we also have to figure out what time is. Or not time, sorry, acceleration. If we can figure out what acceleration is, then we can use the quote-unquote fourth equation, or we can use, moving this around, we can use this equation right here to solve for delta x. So what we need to do is we need to figure out what that a is right there, and once we have that, it's a kinematic equation, fairly straightforward, easy. So how do we know this is acceleration? When they're talking, whenever they're talking about coefficient of friction here, you know it's going to be some free body diagram. It's going to be some forces in the x direction, forces in the y direction, acceleration here. So the first thing we should do is draw a free body diagram for M1 and M2. We'll see later that we actually don't need to know what's happening with M2. It's just with M1 because the stopping distance is how far. It has to do with the acceleration of the mass that is on top. It has to do with the coefficient of friction between that. So if we draw M1, we have the force of gravity 1 down, or M1G. And we have the normal force of 1 up. We want to make sure we distinguish those two because of this idea right here. We have a coefficient of friction, and that coefficient of friction is based on the normal force and the force of friction. We'll go over that in just a second. So if the truck is moving forward and suddenly stops, you can imagine that the beams on there are going to continue wanting to move forward because of Newton's first law. It doesn't keep going on forever because there is some friction, but if it's moving to the right, then the friction is going to be back to the left. What we have with mass 2 is we have the normal force of mass 2, we have the force of gravity of mass 2, and in this case the force of friction, this would be the reactionary force, would actually be in the other direction, because from the perspective of the mass on the bottom, if M1 is moving to the right, then technically it is moving to the left relative, so it's moving to the left, its friction would be in the other direction. But we're really just going to concentrate on this, and we can figure out all we need to based on this here. So let's go ahead and write, so this is our mass 1 here, so the sum of the force in the x direction. I always do right minus left. I know this is different in Ms. Ward-Prim's class where you may just choose whatever way it's accelerating to be positive, just how I did it with my pre-AP. Everything to the right and everything up is positive, everything down and everything to the left is negative. And whatever way this is accelerating, positive is to the right, negative is to the left, positive is up, negative is left. So we have 0 forces here that are to the right, so 0 minus the force of friction of 1 equals M1A. So that's all we have for there. We'll simplify a little further. In the y direction, we have f of n1 up minus f of g1 down equals 0. The reason it's 0 is that although it may be accelerating horizontally, it's not accelerating up and down. I think we stated this before in my class where we will always try to make sure that one block only has acceleration in one of the 2 dimensions here. So we're going to go ahead and solve for f n of 1. F n of 1, if I move f of g1 over the other side, f g1 is really just mass 1 times gravity. So our mass here, let me show you work. So the mass was 10,000 kilograms. Gravity is 9.8. So that's how we get the 98,000 newtons. So f n of 1 is 98,000 newtons. Now the reason that we need that is because the one connection between the x and y direction here is this coefficient of friction here. They give us what mu is. We just figured out what f of n is, or f n of 1. And so if we rearrange this equation here, we can get the force of friction. Clear here. The force of friction equals mu times f of n. And we know mu. We just found out what f of n is, so we can figure out the force of friction. Okay, so we're going to take this equation. We're going to put it down here. 0 minus force of friction, or as what we just found, mu f of n, goes down here, equals m1a. The 0 doesn't really matter here, makes a negative sign, but this mass and this mass here don't matter because we have a mass on both sides. So what we have here is, if we simplify this around, we get A equals negative mu g, and our mu is 0.5, so negative times 0.5 times 9.8, and you get this negative acceleration. This over here is a helpful hint. You will have to eventually kind of prove this here, but the reason that our acceleration is negative, think about it, it's moving in the positive direction and it's slowing down in the opposite direction there, so the acceleration would be in the negative there. That's why that comes out as a negative. If this thing were accelerating forward, that would be a positive acceleration. One thing of calculating is that if you want to know the acceleration on any flat surface, this is your equation here. I mean, we can see that that's definitely what we got here. The only reason it was negative is because it was slowing down. On an inclined plane, it ends up being this right here. We can go over some more problems later as to why that is the case. So once we have the acceleration, we plug it into our fourth equation here. And we solve it, and we get 14.7 meters. So that's how far the truck has to slow down in order for these things to not start to slide for that. So we did not need mass 2. And so what else did we not need? It says, is any piece of data unnecessary for the solution? We actually didn't need to know the mass of the truck. The mass of the truck and the mass of the beams, actually none of the masses matter. We didn't need to look at the mass of the truck because we were only studying the acceleration of the beams, and we did not need to know that. So go back again. So how do we know that? They're asking for some kind of distance. Well, if they're asking for distance, that you should be thinking linear motion. Linear motion says you're going to be using one of the kinematics. The fact that they give you speed and they're asking for distance likely means that you're solving for time or acceleration or something like that. When we wrote out what we were given or what we were being asked for, we realized in order to solve for delta x here, we had to figure out the acceleration, So that's when we say, hey, acceleration, what ties those together? That means we have to do the sum of the forces in x and y. We had our equation in the x. We didn't have enough information, so we had to solve for the y. Once we had the normal force in the y direction, we could plug it into this equation, mu Fn, and then it allowed us to then substitute the basically mu Fn in for force of friction. We went and we eliminated, oops, that went flying. We eliminated some variables like mass, and we showed that the acceleration is only dependent on the coefficient of friction, mu, and gravity. Once we found the acceleration, we plugged it into the kinematic equation to solve for delta x, and then kind of reflecting on this, that we did not need to know the mass of the beams. Even if we took that into account, it would still be negative 4.9, nor did we need to know the mass of the truck itself there, because the normal force from the beams has nothing to do with the normal force or the weight of the truck underneath it. So that is a rundown of number 52 right there. Was a little bit quicker, but like I said, it's video. You can go over that as much as you would like. Let's see what's back here. Hold on. It took about 11 minutes. Let's look at number 53 here. And I'm actually going to use my own working out notes to show you this, because it doesn't take a full, let's say, solution going on here. So 53, so this is my work. I like to use open white paper because I can move around and I can use as much space as I want to, and I'm not confined by it. But here we have number 53. I'll read number 53, and then we'll look at the sort of the diagram that I drew of that. So 53 is up here. It does say review. I've come to learn when it says review, you're going to use something from the chapter before this. And what was the chapter before Newton's laws? It was linear motion, constant acceleration, things like that. So it says a rifle bullet with a mass of 12 grams or 0.012 kilograms traveling toward the right at 260 meters per second strikes a large bag of sand and penetrates it to a depth of 23 centimeters or 0.23 meters. Determine the magnitude and direction of the friction force, assumed constant, that acts on the bullet. So in this case here, this is actually this is sort of opposite of the one we had before, where we had to use forces to figure out the acceleration and the distance. They're now telling us our initial speed, 260 meters per second. They're telling us what delta x is. Our delta x is right there. They're telling us what it's coming to a stop. So there's initial. The final is 0. Delta x is 0.23. So if we write out what we know, and here's my work down here for 53. This is a basic drawing of what we're seeing here. We have a bullet that's being fired to the right. It then goes and penetrates into a sand or something that stops it. We are told the mass. We're told the initial speed, 260, and it's coming to a rest, so that's 0, and we're told what delta x is. So we're actually going to use the same equation, what I call the fourth equation, to solve for acceleration. Whereas the last problem, we knew acceleration, we're trying to find delta x. This one, we know delta x, we could find the acceleration. And when we solve for it, we get an enormously huge acceleration. But if you think about it, that makes sense. I mean, it's going 260 meters per second, which is like 500 miles per hour. It's stopping in like 0.23 centimeters, which is not that far. Let's see here. If I use my ruler, it's stopping in going almost 500 miles per hour, and 0.23 is from there to there. That's not that much. That's an incredibly large deceleration. That's why that's negative there. It comes out as negative. And so really what we're trying to find is what is the friction force? And using Newton's second law of F equals ma, so sorry, F equals m times a, we have our acceleration. They told us the mass, and we multiply the two together, and we get a friction force. Now they told us to give us the direction, so you could either get negative 1,795.88. You could also write it as positive 1,795.88 at 180 degrees, which means on the unit circle it would not be 0, it would not be 90, but it would be facing. And it makes sense. If this bullet's flying into here, the bag here has to push in the opposite direction to slow this bullet down. And so that is 53. Not as bad as 52. Let's now take the time to look at 64. So I'm probably going to, if you can do 64, you can basically do any other pulley problem that's out there. It's just longer. So I will try to try to go through and show it. What I might do is just walk through my work I have here. So I'll redraw the free body diagrams, but then I'll show you my work and how we figured that. So let's first look at 64. We actually did ones like 64 in pre-AP Physics, except we did not have friction between them. So that complicates things a teeny bit, but not too much. So 64 says, I'll just show you the picture and I'll read it. Okay, so it says, 3 objects are connected on a table as shown in this diagram. The coefficient of kinetic friction between the block of M2 and the table is 0.350, so mu is 0.35. I can write that correctly. There we go. They tell us the masses are 4 kilograms, 1 kilogram, and 2 kilograms. And the pulleys are frictionless. It says draw a free body diagram of what each of these look like. Determine the acceleration of each object. Now the helpful thing is like, oh, they're going to have different accelerations. If this cord isn't stretching, which it's not, the acceleration of each of these will be the same. Once we find the acceleration, we'll use the equations that allowed us to figure the acceleration. We'll plug it back into those and be able to find the tension. And this says if tabletop were smooth, would the tensions increase, decrease, or remain the same? So we'll look at that a little bit later. So I'm going to shut the book here, and I'm going to read. I'm going to show you what my work looks like. Let's see if I have the other one here. So this is what my work looks like for this whole problem. So that's a doozy of a problem, but it's not necessarily really difficult. You just have to understand that it's going to take a little while. So I'm going to redraw this table here, but much bigger, so you guys can get an idea of what the free body diagrams are actually going to look like. So there's mass 1, there's a pulley over there. Got another one over here. Okay, so they show us, let me try to represent it in the picture actually, they show this one to be more massive than the one on the right. Okay, so this one is M1. Clean that up a little bit. This is M2, and this is M3. And it says that M1 equals 4 kilograms, M2 is 1 kilogram, and M3 is 2 kilograms. It's always annoying when they use numbers that are really close to what's already up here. So we're going to go ahead and draw the free body diagram here. So that's not contact there. And one of the ways that we did this in my pre-AP class is that instead of looking at this all at once, what I recommend is that you draw boxes around, and if you use colored pencil it makes it easier as well, boxes around the objects we're looking at so that we're just concentrating with what's happening inside of that box. Okay, something like that. Sorry if my hands are I have a little dry skin, so that's the thing about having skin conditions there. But anyway, so let's go ahead and draw the forces that are on here. Actually, before we do that, so M1 is 4 kilograms, so it's more massive than what M3 is. So this is 4, this is 1, this is 2. If this is on a table like this and there's no other masses, there's just 3 in here, it doesn't really matter what's going on up here. If this is more massive than this one, this whole thing is going to rotate in a counterclockwise rotation. So the acceleration here is going to be up, and I'm going to call that positive acceleration. The acceleration here is going to be the left, and I'm calling that negative. That's where we might differ from how AP Physics does it. They might call the left positive, but I'm not going to do that. And then this one is going to go down, so down is negative acceleration, so it's down. So I'm still going to do right minus left equals MA, but just realizing that my A is going to be negative and negative for this one, while it's going to be positive for this. So let's go ahead and draw. Let me go ahead and sharpen this pencil real quick. What happened? Oh, maybe trying to sharpen it. There we go. So I'll use this blue color pencil, and we're going to go ahead and do M1 first. We have the force of gravity of that in the beginning, and I'll just call that M1G. So M1G is just 4 times 9.8. 4 times 9.8 is 39.2 newtons. But we also have, we have to realize we have a tension. We'll call this T1, we'll call this T2. It doesn't really matter what we call it as long as we're consistent. So this is being pulled upward by T1. And that's all we have. There are no horizontal forces on this. It's either moving up or it's moving down. Let's also look at M3. M3 will be very similar to this one, where we have the force of gravity, or M3G down. So M3G, which is 2 times 9.8, which comes out to 19.6 newtons. But we also have a tension up, but it's not T1, it is T2. So those ones, not bad. It's the one in the middle that is a little bit longer. So let's think back. We have the normal force up. I'll call it Fm2. We have, if this were a friction on the surface, it wouldn't matter what's happening with these up and down. The reason why we have to take this into account is because of that equation that we had before, where mu is force of friction divided by normal force. Because there's a force of friction here, we have to take into account the normal force. Anyway, down we have the force of gravity 2, which would be M2G. M2 is 1 kilogram, and that is 9.8 newtons. We have T2 pulling to the right, and we have T1 pulling to the left. But that's not all. We do have friction. It mentions that there's friction, that the coefficient of friction, mu, is 0.35. And we predicted that this object is going to be moving to the left because this whole thing is moving in this direction. So if it's moving to the left, that means that the force of friction is also in the right direction. So that is force of friction for 1, because it's mass 1. Okay? Once we have that free body diagram, it's about setting up and making equations for each of these here. So this is where I'm going to go and show you what I have for my work. So we'll have this somewhere so we can see it bigger. I'm trying to try to fold up some of my paper here so you can see better. So this is our free body diagram. Let me zoom out more here. And refocus. Okay, so we have our free body diagrams as shown there. We have to create equations for each of these here. So I know it's a lot you're looking at once. I'll try to make it easier by just showing you what you need to be looking at this moment here. Okay, so we're looking at mass 1 up here. Okay, looking at mass 1. Mass 1 is 4 kilograms. We're saying that the sum of the forces right and left is 0. Okay, that makes sense. In the y direction, up minus down. Let me refold this so you can see that picture. There we go. Okay, so what we have up and down, we have T1 up minus M1G down, which is right here. Let me just refocus this real quick. Okay, sorry, actually that's T1. We have T1 up minus M1G down equals negative MA. Mass is positive, but the acceleration is negative. So we'll plug in what we know, 4 times 9.8 minus, sorry. I had moved stuff around. So I'm moving stuff around here. I'm moving my mg over the other side, so I'll have mg minus m1a. So 4 times 9.8 minus 4a. I'll take this as far as I can. T1 equals 39.2 minus 4a. Let's go ahead and ignore that for right now. That's something that comes later. And we wouldn't necessarily know what this is right here. Okay, so where we are at this point is just here. So you're seeing some work later. So we are just there. We do not know. Actually, let me cover up this answer because we do not know what this is right now. We'll have to come back and solve for that. I'll also cover that up over here because we wouldn't necessarily know what that is either. Okay, so where we're at this point is that we have T1 equals 39.2 minus 4a. That's all we have at that point. So what we got to do is we have to move on to another direction here. So this one's a little bit more full. I'll try to keep it here. So let's just look at our equation here. Right, we have T2 plus we have the force of friction of 1 minus T1, which is what you see here, equals negative m2a. Once again, it's negative because the acceleration is negative. Now, I rearranged these equations here. I just moved stuff around so that I had T1 minus T2 equals F, force of friction plus m2a. Really, once you get to this point, there's not enough information that we know, so we'll just leave it here. Actually, we'll leave it. We wouldn't, I'm not going in order here. We wouldn't know what that is. So we have to look now in the y direction. Okay? The y direction says we have the normal force up minus m2g. So normal force minus m2g equals 0. I'm going to move this over the other side. Normal force is mass times gravity, 1 times 9.8. Normal force is 9.8. Now, if we don't know what that is. However, we do have this equation down here that links that. They tell us what the coefficient of friction is. We just found out what the normal force is. So if we rearrange the equation and we multiply those, we get a force of friction of 3.43. So once again, we didn't have enough in the x direction. We didn't know what the force of friction was. We could plug in the mass eventually, but we had to use the y direction to figure out the normal force. Use the fact that they gave us the coefficient of friction to solve for the force of friction here. And then what I mean is that then goes up, and that now plugs into here. We still don't know what T1 and T2 are, but we can plug in 3.43 plus 1a. The reason it's plus, what did I do here? Sorry, I'm just checking some of my work here. Is this my work? Hold on. I think I had simplified it a little bit earlier. I think I had recognized that I had made a mistake in my own work, and so this is the one that I did in my last Zoom meeting that got actually cut off. So this is another way of looking at this. So just to kind of reiterate here, we would not know what this is yet. So we have basically in your equation you have T1 minus 39.2 equals negative MA, and then I'm going to move 39.2 over and plug that in, so I get T1 equals this value there. Okay. With M2, I set it up a little bit differently. We have T2 plus force of friction 2 minus T1 equals negative M2A. So we realized there was not enough information to solve for there. We then looked in the y direction, and just as we'd done before, we realized that the normal force is equal to the force of gravity. I had done some stuff here where I had substituted, where am I here? Just right, where I realized up here that sorry, this one I did it in a different order there. I realized the same way we solved it here, that the normal force times the coefficient of friction equals the force of friction. Once I had that, I could plug it back into my equation. To solve it another way is I could realize that the mu Fn is just mu m2 times g, and that plugs in back over there. So this value that I have right here, if I basically go down here, T2 plus the force of friction, which we found was 3.43, minus T1 equals negative 1a. So sorry if that's a little bit confusing. I just realized that Fn of 2 equals Fg of 2. And so according to that, Fn of 2 is mass 2 times g. And I could rearrange that. So we have that's basically what we have right here. Fn of 2 is m2g. I can rearrange this here. That force of friction is mu Fn. And what F of n really is m2g, so mu m2g. So I hope that's not overly complicated. I'm just substituting that. Basically, this is coming down here. This force of friction is going right there. So that's 0.35 times my mass, 1 times 9.8, and that's where we get this. And you're saying, well, that's overcomplicated. We don't know what T2 and T1 are. yet. And so we have to go to the third direction, or the third mass, apologize. So in the third mass, okay, we don't necessarily know what this is yet, but for our equation, the forces in the x direction are 0. There, no right or left. Up and down, they should be T2 minus 19.6 equals positive ma, because the acceleration is positive. We can then plug in what we know about the mass here. Okay, we'll rearrange it here, and we get 19.6 plus ma, or 19.6 plus 2a. And you'll say, well, why do we? What is the whole purpose behind doing that? The whole purpose behind doing it is that we know what T2 is, we know what T1 is, and we have to substitute T2 there and substitute T1 there. The reason is that we're getting rid of these things that we don't know, and we're substituting in an acceleration into an equation with the acceleration. So this is the substitution of that. T2 is 19.6 plus 2a. I recommend you use parentheses. Plus 3.43 minus quantity 39.2 minus 4a. That's why when I distributed the negative, this became negative, that became positive. So minus the 39.2 minus a minus, or plus 4a, equals negative 1a. You move around the numbers and you get 16.17 divided by 7a, or a is 2.31. Okay. So once again, just kind of review how I went over this here. I was just trying to show you that I can substitute what we know about the x direction into the y direction and vice versa. Once we have what the acceleration is, to find the tension, we just plug in the accelerations up into here. So 39.2 minus 4 times 2.31 is 29.96. And plugging a into here, 19.6 plus 2 times 2.31 is 24.22 newtons there. Okay, so it's kind of a longer, complicated one. I apologize. I was looking back and forth. I realized I had made a mistake in my work, and I forgot to check myself on that. This is the one I showed a student we were doing Friday. We were able to walk through it here. So I'm trying to, once again, just to go over what's going on here. I wrote my equation. So this is to the right, this is to the right, this is to the left. The whole box is moving to the left. Normal force up, force of gravity down are equal. So I realized that Fn of 2 is equal to Fg of 2, or m2g. I rearranged this equation for that, and I get force of friction is mu times F of n2, and F of n2 is m2g, so mu m2g. So I plug that back into here. That became that. So T2 to the right. I substituted mu, m2, which is 1 kilogram, and 9.8. Rearranged it, or just plugged in what I knew. And then I had an equation with T2, T1, and A. I substitute in these, and it leaves only an equation with A. So A there, and A there. You separate the variables out, and you get an acceleration of 2.31. And then once you get that, that goes right back into here to find the tension, and that goes right back in here to find the tension as well. So hopefully going over that the second time, but I'll just leave the free body diagram that we have here with that. So I think I'm going to call it at this. I don't want to make this video too long. I think I went about as long. It's a little bit shorter than. Hopefully, oh, it is going to record because it's not through Zoom. It's through my document camera. So. Hopefully that helped. If you have questions, obviously Ms. WordPrem is there, but I am here as well. I have a video already up on the BHS AP Physics Schoology group that has, let's see here, it has like 6 different problems on there. So if you have troubles with those, go and look at those as well. I might be making another video tomorrow with some other problems, but it's all about whether or not you guys are interested in that or not. So this will be linked to my YouTube page because these files are too big for Schoology. So appreciate it. If it helps you any bit, let me know. If you need any clarification, also let me know. It does take up time, but I'm willing to do it for you guys. So Have a good evening, and I'm signing off. Mr. Dahlstrom.